Well, my student, today we shall discuss about the scattering of particle in quantum mechanics. Basically, we will try to develop a very basic general theory on which the scattering phenomena can be viewed, can be analyzed in mathematical forms, and we can get the details of the physics behind the phenomena. Particularly, this topic that we are going to discuss in detail will be presented roughly in three parts: part 1, part 2 and part 3. Part 1 will describe the general description and some definitions. In part 2, we will develop the main motive of our general theory, how the phenomena can be represented mathematically. In third part, we will go over to the observable that we will measure, how that can be defined and how that can be related to some quantities which are associated with the scattering phenomena, mainly the wave functions and others. So, let us start stepwise. So, we shall start our first part, that is general description and definition. Now, let us begin the scattering of particles. What type of scattering actually we want to deal in this class? As because the chapter is confined with the quantum mechanics, so it is a subject where scattering of subatomic particles will be considered mainly. Subatomic means like photon, electron, neutron. These will be taken as the incoming or incident particles. Also, we can take a choice of atoms, molecules as incident particles, and they will fall on a scatterer. Scatterer may be of various type. It may be atom, maybe a single electron or single neutron or photon. Whatever it be, it may also be a solid cluster of particles. It may be a gaseous system, it may be a liquid system. So, whatever be the choice of scatterer, we try to concentrate our attention in this way, that it is nothing but an approach that we will develop theoretically that deals with the scattering of subatomic particle or very teeny particle like atom or molecules that will be scattered by some sort of another system which we call collectively as a scatterer. Okay? So, now let us start with, firstly, have an idea. Let us try to have an idea how the scattering experiment can be viewed, or in laboratory how scattering experimental setup is designed. So, let us see. So, schematic view of scattering experiment. In actual practice, in case of scattering experiment, what is used and how it looks like, let me try to discuss something about that, so that we can all have some knowledge and we can focus our attention to the subject. What is it? Now, this is a source of particles which are directed towards the definite direction, and this system, we all know that it is nothing but a selector which selectively pass some sort of particles will allow to go in a particular direction. What we call it? We generally call it as the incident beam having definite momentum or definite energy. Now, when this incident beam hits a target, which we call it as scatterer, and this is your incident beam. So, incident beam is made to fall on scatterer. What we will observe? That incident particle is now scattered in various directions around the scatterer. So, these are the part of the incident beam which have been scattered all around the scatterer. Suppose one of such scattered beam is going in certain direction in which we kept a detector. So, it is a detector. What's the function of this detector? The detector, it detects that how many particles is scattered along this direction, or what fraction of the incident beam has been scattered along this direction. Detector is a counter, it's an electronic device which just note how many particles are entering or being scattered along this direction are. Now, in this experimental setup, what we say that a monoenergetic incident beam is made to fall on a scatterer. That scatterer scattered all the incident particles into various directions. One of such direction, say it be designated by a radius vector r, and it is obvious that the scatterer is taken at the origin of the coordinate system. Usually we do so. This is the experimental arrangement. Of course, it is schematic view. I am not drawing the whole apparatus, just the principle on which an experimental setup is designed. So, is it clear to you? I think now, in developing the theory of scattering, we need some additional feature. Actually, with the help of this second picture diagram, it will be very clear to you that how scattering occurs and how it is measured mathematically with the theory of quantum mechanics. So, say it is the z direction, z axis, which is the direction of incident beam. Incident direction. Now, let us consider a plane this is your xz direction. So, if we draw this plane, this gives you, it is a plane of xz. So, it is xz plane. Actually, in our theory, we try to express this xz plane as reference plane. Reference plane. Now, if a particle is scattered, say in this direction, at an angle of theta with the incident beam direction, so what we will get? We can have another plane. We can draw another plane containing the scattered beam. So, this is your scattered beam, incident direction, and it is a plane. If we demarcate it with new colors, say this green dotted plane is called scattering plane, the plane of scattering, scattering plane or plane of scattering. So, it is a scattering plane. So, scattering plane is the plane containing the incident beam direction and the scattered direction. And if the orientation of the scattering plane and the reference plane, we can get an angular position which we usually call it as the azimuthal angle. So, phi is the azimuthal angle to indicate the position of scattering plane, the position of scattering plane with respect to the reference plane. So, now if we like to draw a cone of this form, then this cone is known as scattering cone. Scattering cone. So actually this is the diagram which we need to express the scattering phenomena. Now based on this pictorial view, next we will go over to our next topics, that how the scattering, the detector, how detector measures the number of particles that entering in the region. That is our main objective, and we will go over to that subject just now. Now let us pass over just to define our observables that need in our scattering theory or scattering experiment. The observables are scattering amplitude, and cross section. Of scattering amplitude and cross section. Now topics 2. Scattering cross section and scattering amplitude. This is our main target, and finally we will try to represent these quantities in terms of our wave mechanics or quantum mechanics. And before going to that quantum theory, let us have an idea of what does the cross section tells in terms of classical concept. As a student of physics, we all know and we are always familiar with so many consequences and processes where we need to consider some assumptions depending upon which the total theory can be developed, or a modeling of the system can be viewed. Basically, we need. So, let us start with the basic assumptions. In scattering process, there are three things that to be taken into account in our discussion or in our mental frame. One is your incident particle or the projectile. Secondly, the scatterer that will scatter off the incident particle in various directions. And the third one is our detector, what it measures, most desirable observables like cross sections and other things. So, in everywhere there are some limitations, there must be some restrictions while we will go to solve out the problem, when we try to visualize the total system as a whole. So, basic assumptions that I am trying to say now is the first one, steady incident beam. Steady incident beam. Steady incident beam means it is a requirement of the scattering processes. Steady incident beam means the number of particles, I mean the projectile, the number of particles crossing an unit area in unit time is constant. Constant means it is independent of time. So, the first point of our basic assumption is to consider a projectile beam of such nature that the number of particles that is coming towards the scatterer will remain unchanged or remain constant with time. That is, time independent beam will be allowed to fall on the scatterer. So, this is our first basic assumption. Our second basic assumption, that the number of incident particle and the number of colliding, I mean the number of scatterer would have to be very low. Why is it so? If we consider a large number of particles coming in unit time towards the scatterer, which also contain a large number of particles, then at each collision, the collision will not be confined to a single type of collision. That collision may be multiple type. So, in order to grip our system in our hand, we like to focus such a system of interaction where every interaction will be a single two particle collision. Single means one collision. Two particle means one is your incident particle, incident or projectile, and one scatterer. Means only one atom or molecule or any subatomic particle, whatever may be. In the collision process, in every single encounter, only one incident particle will interact with one target particle or one particle of the scatterer. Okay? So, these two as the basic assumptions on which we will try to develop our detailed mathematical description. Okay? Depending upon these basic assumptions, we will try to discuss about few definitions of necessary or important parameters. Few definition. Firstly, incident flux J. We call the incident flux J as the number of incident particles, crossing an unit area held normally to the incident direction in unit time. So, it is the number of incident particle passing or crossing an unit area in unit time. This is called the J in, the incident flux. Second definition, number of scattered particle in unit solid angle in unit time is called N. So, N is the number of scattered particle, actually the particles which are entering to the detector in unit time, in unit solid angle, that we call it as N. From these two particular definition of the two types of particles, we pass over to third one is your differential cross section. Now, differential cross section is defined as d sigma d omega as the differential cross section d sigma by d omega as the ratio So, N by J, the ratio of number of particles entering into the detector to the incident flux J. This is called differential cross section. So, detector usually is a counter which counts this figure directly, that is called differential cross section. From this differential cross section, we can easily calculate our total cross section. So, total cross section is nothing but the sigma, which is the integration of the differential cross section over the whole solid angle. That means when detector can move through all the scattering angular positions and through this azimuthal positions of the scattering plane, the sigma is nothing but the integral d sigma d omega, that is differential cross section integrated over the whole solid angle d omega, and this will integral 0 to twice pi d phi integral 0 to phi d sigma d omega into sin theta d theta. The radial part doesn't come into this relation because of the fact is at a point from which we consider the origin of the coordinate system, and detector is placed at somewhere which is at a distance r or which is designated by the radius vector r. So, as r can be taken constant and it can move all around, then while considering the integration over d omega, the disappearance of r is obvious to us. So, this is the differential cross section and total cross section. Okay? We are going to discuss about the development of theory. In considering the scattering processes, we must consider that the scattering phenomena only consider the following character. One, it is your time independent phenomena. Time independent phenomena. So, necessarily we will pass over to time independent Schrodinger equation. So, if it is time independence, means that potential the incident flux must be time independent. Scattering phenomena is of elastic type. So, it is elastic. We will consider the elastic type of scattering. That means where energies remain unchanged or conserved. So, this is the characteristics of the scattering processes that we like to consider in our theoretical development. Master equation, which we call the Schrodinger equation. So, h cut square by twice m del square plus v of r psi r, or if you try to express it in more general, then it will be r theta phi, which is your E psi. Where m is the mass of incident particle, V is your interaction potential, E is the energy of the incident particle, energy. It has a definite value of this type, half mv square. Also it can be written as p square by twice m. It can also be written as h cut square k square by twice m. This v is your velocity of the particle, and this v is the potential. And when that particle interacts with a potential, and psi represents the total configuration of the state. So it is the state function. We all know that whenever we try to solve the differential equation of this type, that is the Schrodinger equation, we need some boundary condition. Unless we impose any boundary condition, we cannot have a solution which will match to the situation. That in order to have a solution of psi, we need some boundary conditions. What would be the boundary condition to solve such a problem? Boundary conditions. And the boundary condition must be such, it must have a relevance with the physical situation. Firstly, the interaction potential would be such that at large r, that is far away from interaction potential, V of r must go to 0. At the second boundary condition, at large r, the total wave function representing the scattering process as a whole as a whole must contain two parts. One is your incident wave, the wave representing the incident beam, as well as a scattered wave function representing the spherically outgoing scattered wave. So, these two are the basic boundary conditions. Let us have an idea with a picture, diagram. Let us have an idea with a diagram. It is your incident beam. Suppose there is a scatterer. After the scattering, scatter beam will scatter in every possible direction around the scatterer. Now, this scattered beam can be represented by such spherically oriented wave. So, this is your spherical wave to represent scattered beam. And this is your incident beam. So, at a large distance, what will happen? We always expect the final psi may contain the sum of these two. One is your scattered wave and another is your incident wave. So, it is your incident beam or incident wave. If we like to represent the incident beam as a parallel beam, then obviously it is your plane wave. So, incident wave is your plane wave. It is your plane wave which represent the incident beam, and the scattered beam is represented by spherical wave. So, the incident wave function psi in is generally represented by the plane wave. So, we may write it as A e to the power I k dot r, and if we take the direction of incident be z direction, then it will be e to the power I k z. Of course, it is a function of r. The scattered beam can be represented by a spherical wave. So, scattered wave can be represented as, say, e to the power I k r by r. This represents your spherical wave, and any wave function must have or may have some amplitude part. Say this is your f, and this f, which is the amplitude, is known as scattering amplitude. So, scattering amplitude is now came to our knowledge that it is nothing but the amplitude part associated with the scattered wave. If scattered wave is represented in a spherically symmetric wave, that is a spherical wave. So, with this spherical wave representation, the amplitude part is called your scattering amplitude. So, final psi must have two parts, psi in plus psi scattered. Incident part is taken as usually as the plane wave, and any plane wave is represented mathematically by this form, and the scattered part is taken as your spherical wave. Because of the symmetry, it may happen that the spherical wave we cannot have. Why it may happen? If the potential function is such complicated, then we cannot have such a simple form. So, this is the simplest form which we try to focus here because of the simplicity. As a beginner, we will start from this simplicity, or the simple concept. So, from this simple concept, we are now at a time that how incident beam, scattered beam, etc. can be represented mathematically, and why it is of plane wave and why it is of spherical wave. I think it is now clear to you. So, what we have done up till now? We have only have an idea how the scattered beam and the incident beam are represented in terms of wave mechanics. Now, we shall try to focus our main objective to find the cross section in terms of quantum mechanical view. Scattering amplitude is now become clear to you that it is nothing but the amplitude part associated with the scattered wave, which we taken here as spherical wave. So, scattering amplitude is clear. Now, let us come to the representation of cross section. Already we have some idea about this term, that is cross section, in terms of in the classical view. So, let us write how this cross section can be represented in terms of this wave function, the mathematical form. Okay. Now, let us try to write the scattering cross section in terms of your mathematical formula, out of the wave function theory. We all know in spherical polar coordinate, the delta is represented by, we all know it, still I am writing, it is del del r plus 1 by r del del theta. Of course, we can put here a unit vector of this type. All this is known to you. Now, let us call the probability current density, probability current density J can be written as h cut by twice mi that is your psi star del psi minus psi del psi star. By the demands of demand of asymptotic condition, asymptotic boundary condition, we only need the radial component, of J scattered. Radial component of the J scattered that is J scattered R is important to us. So, therefore, J scattered, radial component of J scattered is nothing but h cut by twice the mi psi star, of course scattered wave, it should be del r of psi minus into del r of proceed in this way. The psi scatter can be represented as f theta or theta phi in more general form. If we write it in terms of theta and phi, so it is f theta phi e to the power ikr by r. So here we substitute this psi and get back the result. To consider I psi star del r of psi minus psi del r of psi star. So f theta can be taken out as f theta square e to the power minus ikr by r multiplied by del psi of this means there we will get ik divided by r it is a minus 1 over r square with e to the power ikr. So this is the first term. Likewise for the second term, we can write easily that e to the power plus ikr by r minus ik by r, again minus 1 over r square e to the power minus ikr. So we can write it in this way, f theta phi square, and e to the power ikr and plus and minus, it will give you 1. So taking common all e to the power function, exponential functions, is equivalent to 1. So no need to write them. Exponential part, I can write it e to the ikr by r square minus 1 by 1 over r cube minus plus, so it is ik by r square, and it is your now these two goes. So we will have finally this much, that is twice ik by r square. If you try to write the full form of J scattered, r, it will looks like h cut by twice mi multiplied by twice ik by r square into f theta phi mod square. Now it will become as h cut k by only m r square. What is it? It is the expression for radial component of J scattered. Let us write it as A. Now let us proceed how to represent this in terms of your scattering amplitude only. So for that, okay, if this is the radial component of J scattered, that is the radial component of J scattered, which is crossing through a cross-sectional area of say d sigma, and the particle has the velocity v in unit time, this will be the dimension of the scattered beam length. So from this diagram we can write that J scattered, radial component of J scattered, when it will be multiplied by r square d omega, will give you v times d sigma. So d omega is your concept where we kept the detector. So detector have a very small solid angular confinement of d omega. It is the detector. So if J square J SCR is multiplied by R square d omega gives you the number of particles entering into d omega in unit time, and that must be equivalent to the V into d sigma. D sigma is the cross section. So therefore, quite naturally, d sigma d omega, that is the differential cross section, must be equal to J SCR d sigma d omega J SCR R square by V. Again, we know that V can be written as H cat K by M, H cat K by M, M it will go up. So the expression would become M R square by H cat K J SCR. So it is expression B. Is it clear to you? I think all of you can easily follow. Nothing is hard, very easy. So comparing this A and B, this is your this much M R square by H cat K multiplied by, if we put these values, it is your H cat K by M R square into J scattered radial component. So this will be F theta phi mod square. So this will becomes F theta phi square modulus. So differential cross section. Now we come to the almost at the end point of this term, which represents the observable differential cross section. This sigma omega can be found directly from the square modulus of scattering amplitude, and it is the most vital and the important relation. Now after having this equation, we can easily pass over to total cross section. Now let us have an implication of this term. Now when the detector is placed somewhere in the experimental setup, what it do? The number of particles going there, and this counting is called the differential counting. When the detector moves all around the scatterer in every possible direction from your angular, the scattering angle variation, and also with the azimuthal variation, we can calculate the total cross section. So total cross section is nothing but the integration of this term over the whole solid angle. So how it can be represented? The total cross section sigma is our integral d sigma, that is integral d sigma by d omega over the whole solid angle. And if we write it in terms of our polar coordinates, spherical polar coordinate, integration over 0 to twice pi, integration over 0 to phi, your d sigma d omega sin theta d theta and d phi. So let us put d5 here, no problem. So once you can evaluate this integral, we can get the value of total cross section. So total cross section is nothing but the total number of flux all around the scatterer. So I think that up till now what I have told to you, it is clear to you, and let us recapitulate that what we have learned today. From the beginning, we have started to know what is scattering phenomena, how it can be represented, or how we can think it in terms of quantum mechanical view, and in doing so, how the representation for incident and the scattered particle be done mathematically, and what are the basic assumptions are there behind the scattering theory. Also, what are the boundary conditions in having the solution of Schrodinger equation. And after having the solution of Schrodinger equation, we find that the cross section, differential cross section, is directly related to scattering amplitude, and from that relation we can evaluate the total cross section. So this is our end of today's class. So I wish you all the best. I think you will give some questions or another tutorial in our next class.